All right, so here in this video, and to wrap up this module here, let's take a look at some properties of inverses. All right, so we're going to look at some properties and prove a couple of theorems here. All right, so we're going to look at properties of inverses. All right, so now the first one I want to show is, so we're looking at in our book, it's titled Theorem MIU. And it says a matrix can have at most one inverse. So in other words, matrix inverses are unique. Matrix inverses are unique. All right, now in order to prove this, right, a strategy here when proving that something is unique is to assume there's two of them, and then in the process of just kind of working through the fact that your assumption that there's two of them, you'll show that those two are actually equal. And what that does is it proves that it's unique, right? That there can't be two, right? Even if you assume there's two, you find out that's actually the first one. So let me explain what I mean by that, right? So here for our proof, we'll start off with supposing that A is an invertible matrix. All right, this needs to be our assumption because this theorem only applies to matrices that have inverses. So A is invertible with matrix inverses B and C. So both of those satisfy the definition of it being a inverse, right? In other words, I want to take a product of A times B, right? If they're both inverses, right, then AB is BA is IN, right? And the same thing for C, right? AC times CA is IN. Okay, so we'll start with, let's say, all right, we'll start with B, right, the inverse. So B can be written by I times N, right? It's like multiplication by 1, right? So here we said matrix multiplication of the identity matrix, right? So we'll say ID matrix multiplication. All right. Well, now let's use our assumption here, right? Since here I times N can be written as here, I'll write it as A times C. And this is just substitution or definition of an inverse. Okay. And now I also know that I can associate these are all square matrices, remember? Right? They all are n by n. So I can associate them and the product is still defined. Okay. So associativity. Right? And again, as you work through your own proofs, right, one thing to realize is that, right, you don't need to remember the exact wording of the theorem, just the property itself, you can describe it, and that's just as good. And now let's do another substitution here, right? What is BA also equal to by assumption? It's the identity matrix, right? So assumption or property of the inverse. But identity times any matrix is that matrix itself. So we get B. our final result here is B is equal to C. In other words, the inverse matrix is unique, or A only has one inverse. If it has one, it will have exactly one. Okay, so straightforward proof here. Okay, let's look at another property, right? The next property we're going to look at is theorem SS. And this is inverse of a product. Okay. So, and I'll speak briefly why he calls it SS. He gives it an analogy, which is helpful to think of when thinking of this theorem here. All right, so it says, so theorem SS, so inverse of a product. So it states that suppose A and B are invertible matrices. Are invertible matrices of size m. Then AB is invertible, so the product is invertible. And the inverse of AB is B inverse A inverse, right? And here that shows up again, right, as in our transpose properties, right, where the order is flipped around when we apply this, in this case, the inverse, right, in the previous case, the transpose here. All right, so let's see why this has to be true. Okay, so again, really, we just have to verify here that the inverse of this is equal to that. Well, I know since I know A and B are invertible. So really what I have to do is I have to say, all right, let's see. Excuse me. Here. All right. Okay, so we'll start with B inverse A. So here's our proof. All right. Okay, so we'll start here, right? So again, what does it mean for it to be an inverse? So if I want to show that this is the inverse of AB, well then their left and right products need to be the identity. All right, so let's start here, right? So here, I can associate them however I want. So what I'll do is, or not however I want, excuse me, I can associate as long as I keep the order the same. I can do whichever product I want, as long as the order is consistent. So I'm going to associate the middle ones. All right, so here this is just associativity. All right, well, since A is an inverse, I know A and B each individually is invertible. So here, that means that this is the identity. Right, and again here, whichever way you want to associate these here, right? So this is definition of inverse. All right, doing this now. This is just B inverse. Right, so multiplication by matrix identity. And now again, definition of inverses, B inverse times B is I to the n. Okay. All right, and that's just definition of an inverse. All right, so that again, we need to test both sides. So now let's look at the other side. AB times B inverse A inverse. Okay, and then here, really it's going to be the same exact proof here. All right, so here we'll get associativity. So let's do the middle two first. All right, so we get A-I-N, so associativity. All right, and now here the products here of multiplication by the identity. And then definition of the inverse. So now we have B inverse A inverse is the inverse of AB. Right, now the author calls it socks and shoes, right? If you think of why it's necessary for the reversal of the products, right? If we think of us undoing something, right? So SS standing for socks and shoes. So you put on your socks, then you put on your shoes, but what do you do to undo that operation? You take off the shoes first and then the socks, right? Hence that analogy he's making here for SS, right? When you undo it, right, but the order is switched around, but it undoes your initial action. Okay, all right. A couple of other properties here will state without proof, right, but maybe it might be a good exercise to prove a couple of these, right? So theorem, so I'll just state them here. Theorem MI, and that simply states that the inverse of an inverse is the original matrix A. Right? So the inverse of the inverse returns A, right? If you're undoing, which you already undid, then you're right back where you started. Right? So theorem MIT. Right? So what this states is that the inverse of a transpose, so a transpose inverse is equal to the inverse, and then you take the transpose of it. All right, now that's a nice little result here, right? Because if you already found the inverse of a transpose, of A, and you want to find the inverse of the transpose, well, you just take the transpose of the inverse, and you're done. So that's a nice little result here. All right, and then lastly, theorem MISM. Right, so this states alpha A, where alpha is some scalar. So across the inverse, we think of the inverse operation for scalars is really just take the reciprocal. Okay. All right, and those are just a few properties of matrices. We'll be working a lot more with matrices, right? So it's important to just kind of be comfortable working with them, right? In particular, multiplying them, talking about their inverses, or finding an inverse, right? And then we'll see how we apply them in future sections.